So let's take a few minutes and look at quadratic functions and sort of start exploring what they are and what we can do with them. To begin, let's review all the kinds of functions we've looked at so far this year. First of all, our first function of the year was linear functions. And hopefully, if you remember right, our basic equation for those was that f of x is equal to mx plus b, or just y equals mx plus b. And when you looked at those graphs were simply straight lines. Okay. And then when you actually went to graph them, so when you graph them, it just looked like a straight line. For example, it might simply be just like that. The next function we looked at was exponential. If you remember, we talked about exponential growth and decay, and our basic functions looked something like this: a times b to the x power. And that graph was a curve. And that curve would have looked something like that. You'll notice it starts relatively straight and then makes a single curve. Finally, we're going to start looking at our newest version of a function, which is the quadratic function. Now, the equation for this is something we've actually been working with. As we started to look at all of our factoring, we looked at the equation ax squared plus bx plus c. And that is our generic standard equation for a quadratic function. And if we think about the graph, we can sort of see maybe a little bit of a progression from straight lines to curve, and then maybe from a curve to something new. And in this case, what we're really looking for is a special curve. In fact, it's a U-shaped curve. And this U-shaped curve has a special name. It's called a parabola. And when we look at the graph, our graph is going to look like a U-shaped curve. For example, this one, or maybe even this. And so that's our third function that we'll be dealing with, these quadratics. So let's start taking a closer look at what exactly a quadratic looks like and how we can interpret this equation here and use it to sort of get an idea of what our graph's going to look like. So the standard form of a quadratic function is this ax squared plus bx plus c. That's the same trinomial equation that we've been working on for factoring. So let's sort of take a closer look at this standard form. The first thing really to ask ourselves is, what about this form, ax squared plus bx plus c, defines being quadratic? And in this case, the one thing that stands out is this exponent. When we looked at linear functions, we had mx plus b, which had an exponent of 1. And when we looked at exponential functions, we had a times b to the x, where the exponent was the variable. So we had a variable of 1 and a variable of x. An exponent of x and an exponent of 1. Quadratic functions have an exponent of 2 as their highest power. And in fact, that's actually the basis for defining a quadratic. If the highest power, or highest exponent, of a variable in the problem is 2, then you have a quadratic function. Next, let's look at what all these things tell us. Let's start by looking at the value of a. A is going to tell us several things. Number one, a tells you the direction of the graph. And when we talk about the direction of a graph, what we're really asking you, or discussing, is what direction does it open? Does it open up or down? A greater than 0 means that the graph opens up. If I were to sketch that out, we would simply say that, well, here's our coordinate plane, and our graph would open pointing upwards. A less than 0 means that our graph will open down. And just as you might imagine, it will look just like this. We have our coordinate plane again, and now our graph opens down. What's really neat is that A also tells you a few other things. Specifically, it tells you whether the graph has a minimum or a maximum. So if A is greater than 0, then the graph opens up, and then the graph has a minimum, or a min. For A less than 0, the graph opens down, and the graph has a max. When you look at your actual graphs, you'll be able to see these by considering what's going on here. If you think back to domain and range, remember minimums and maximums are the highest and lowest points on a graph. So in this case we have a maximum if A is less than 0 and a minimum when A is greater than 0. The minimum makes it the lowest point on the graph, whereas the maximum makes it the highest point on the graph. The last thing we want to look at is the value of C. One thing that the standard form of a quadratic function has in comparison to a linear function is that it gives you the y-intercept. In this case, C is going to become our y-intercept. Think about it this way. Whenever you have a y-intercept, you know that x equals 0 at any y-intercept. So if you input 0 in for x, you get a times 0 squared plus b times, well, 0 plus c. We know that any number times 0 will go away, so we're left with just the value of c. When we put that into a coordinate point, we know our x value is 0, and our y value has to be c, because that's all that's left. So the c value in ax squared plus bx plus c gives us our y-intercept. This is going to make a lot more sense when we start going into examples later on in the unit when we talk about quadratics, graphing, and factoring, and finding solutions. Speaking of solutions, let's take a moment to kind of talk about what a quadratic function has for an answer and what we call them. So the first thing to understand about quadratic functions is that they're a little different than everything else that we've solved for. In this case, quadratic functions have special answers. And those special answers are called roots. Now, a root is kind of special, and there's several parts of it, but let's sort of take the basis of it like this. Roots are really the answers to a quadratic function. Now, one of the things you're also going to hear, along with the word roots, is that you'll hear that they are also called zeros, or occasionally they'll be talked about as x-intercepts. Now, while these aren't technically incorrect, they're not really optimal. And I'll tell you why. Because there's a one-sided relationship. Think about it like this. Imagine you have a square, and then you have a rectangle. What is it that defines a square and a rectangle? For example, a square has 4 90-degree angles. Okay, what about a rectangle? Well, a rectangle also has 4 90-degree angles. Well, what else is the same? Well, for example, a square has 2 sets of parallel sides. Okay, so we've got that side's parallel and that side's parallel. Well, so does a rectangle. So we've got one set of parallel sides and a second set of parallel sides. And that's pretty good. Finally, a square the length of all the sides is the same. So this side, this side, this side, and this side are exactly the same. For a rectangle, only each of the two sets has to be the same. So for example, these two sides are the same, and these two sides are the same. When you put all this together, you come up with a simple fact, that a square meets all the requirements to be a rectangle, but a rectangle doesn't meet all the requirements to be a square. That is, every square is a rectangle, but every rectangle is not necessarily a square. And that's the same thing that happens with the words roots, zeros, and x-intercepts. While every x-intercept and zero is a root, not every root is a zero or an x-intercept. Now generally this is going to come up more in Algebra 2 and later on, but we want you to make sure that you understand that just because it's a root doesn't necessarily mean it's a zero. There's more to roots than just zeros. So in this class, remember, we're going to use the word roots for most of our work. So when is it that roots happen? Well, it's pretty straightforward. Roots occur whenever a value of x makes that function ax squared plus bx plus c equal to 0. That's the key. And if you notice, that's also one of the reasons why we sometimes call roots zeros. For example, let's take this example. X squared minus 3x plus 2. If we were to evaluate this for, say, the number 1, we'd get 1 squared minus 3 times 1 plus 2. 1 squared is 1, minus 3 plus 2. 1 minus 3 is negative 2. Add that to 2, and you get 0 back. So the value x equals 1 is a root for this problem. If you did the same thing with, for example, 2, you could say that, well, 2 squared minus 3 times 2 plus 2 becomes 4 minus 6 plus 2 becomes negative 2 plus 2 becomes 0. So the value of x equals 2 is also a root for this problem. So any value of x that makes the entire function equal to 0 is a root. Now we're going to find these mathematically, but you can also find them on a graph. When we look at a graph, there are several things we can look for. Specifically, you'll remember that I use the words x-intercept to describe a root. So for example, if we had a function that was drawn like this, we could also look for those x-intercepts. In this case, there's an x-intercept here and an x-intercept here. If we pretend that I could draw perfect lines, we might say that our roots were x equals negative 3, which is this point, and x equals negative 1, which is this point. You could also, for example, do it again, and we'll say that there's our second one, and we'll pretend it intersects here and here, and say that the roots of this function on the right might be x equals 1 and x equals 4, which would be this point and this point, respectively. So the other way to think about it is that whenever the graph of the function, so the graph of the function, touches our x-axis, we get a 0, or a root. Okay? Root is the key word here. So let's think about how roots relate to each other. So let's think about how parabolas can interact with a graph. If we had a parabola that does this, we could say that, well, this has two roots, a root here and a root here. We can't quite tell exactly what those numbers are, but it really doesn't matter. Same thing happens if we had one where the a value is negative. It could cross 2 times. Now there's another option for how it could work. We could have a graph that starts here, comes down, and then goes back up. And if we were to look at this really, really close and zoom in, we might see that it only touches the x-axis once, right there. Same thing, we could have a real narrow graph that points downwards that does the exact same thing, in which case there's only a single root for this problem. And finally, as we're looking at this, we could have a third option. That is some graph that never actually touches our x-axis, in which case there's no root. So those are our three possible options. We have option number one, and this is a set of graphs that have two roots because they intersect twice. The second option we have is that it only intersects one time, in which case we have a problem with only one root. And finally, we have our last scenario where it never intersects, so there are no roots. Or you could go ahead and just say there are 0 roots. And those are the three possible numbers of roots for any one of these quadratic functions.